The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today we're going to talk about building an effective Hamiltonian that enables us to fit spectra. And let's start out with an important question. The effective Hamiltonian, or the exact Hamiltonian is an infinite matrix if we choose to use linear algebra. Why is it infinite? How many basis functions do we have for a diatomic molecule? Did I hear a murmur?
Infinite number.
An infinite number. Why are there an infinite number of basis functions? Yes.
Because there's an infinite number of solutions to the Hamiltonian.
Well, yeah, you're just sort of
Hamiltonian.
So we have an infinite number of electronic states, and each one of them has an infinite number of vibrational levels when you include the continuum, and you have to. And so if we want to describe the energy levels that we would observe in a spectrum, we at least start out thinking in terms of an effective, an infinite matrix. And this is a terribly disturbing sort of thing because we know we're not going to do anything useful with an infinite matrix. So instead we ask, well, how do we describe the little bit of all possible spectra that we're going to be interested in? So, you know, it's tempting to forget that the spectral region that we're interested in, we being sort of a generic we, whoever you are, you go into the lab and you say, okay, I'm going to record some spectra. And you might be an electronic spectroscopist, and so you are concerned with the region from, say, 20,000 wave numbers to 50,000 wave numbers, just because that's where your experiment works. Or you might be an infrared spectroscopist who's interested in, say, 1 micron to 20 micron spectral region, because that's where your spectrometer works. Or you might be a gamma ray spectroscopist who's interested in nuclear structure. And there's all sorts of spectroscopists, and they all look at molecules and they all think they're doing the same thing, but they're not. And so the first thing you want is something that will describe the little tiny piece of spectrum that you're interested in to the accuracy at which you can make measurements. That's the thing if you're an experimentalist, that's what you most care about. Now, it would be useful if that representation of your spectrum can be shown, can be related in some way to something that someone might calculate. And so there's two goals, and they're not necessarily the same. One is, let us describe the spectrum to measurement accuracy with a minimum number of parameters. And we would like to know how those parameters relate to something that someone might calculate if they were demented enough to calculate. But
those are two different things.
Two different things, but any generation of a fit model that will describe the spectrum should keep in mind that somebody might actually want to know what those parameters mean. And so they might want to calculate them. Now, the kind of spectra that we do we being almost everybody in the room, is typically measured at an accuracy of about 3/100th of a wave number, or 1 gigahertz. Now that is much higher accuracy than quantum chemists could calculate, use to calculate any of the properties that we're interested in. So there's not an issue of expecting the quantum chemists to calculate what we measure, but we would like them to be able to get close. We would like them to know what it is that we've actually measured, so that they can get as close as they can with the computers and techniques they have available. So I'm going to describe the procedure by which we derive a finite dimension effective Hamiltonian that we use to fit a spectrum. And we can fit the spectrum with a minimum number of parameters. The parameters have some physical content. We know what they mean. And if we could get a quantum chemist to listen to us, we could tell them what they mean. But usually, they listen to only the words. I have calculated the rotational, I have measured the rotational constant. They say, okay, I can do that. But what they calculate is not what we measure, even though they call something the same thing we call. They use the same words to describe different stuff. So we're going to try to understand why the same words are used for two different things, and how to make a connection. Okay, so the last time we had been talking about, well, not the previous, the next to last time, isolated states. And sometimes they were groups of states. So this was to introduce you to the Hamiltonian for something that we call a multiplet state, 2s plus 1 lambda omega. And sometimes there were groups of states that were natural groups of states, not just pedagogical groups of states. For example, we had a doublet pi state and a doublet sigma state, and they could have been generated by one electron with an angular momentum of 1. And I neglected to say the magic words pure precession. If you have one electron in a p orbital, and that p orbital is weakly interfered with by the ligand, then it splits into a pi and sigma. And when that happens, we think we can evaluate matrix elements that involve L plus and L minus operators. And so that's why we call it pure precession, because we put in some stuff that we're really not entitled to. But this is also appropriate to Rydberg states, that you might have a P complex or a D complex, and the relationships between the perturbation parameters, the interactions between what would normally be isolated states, we say there's certain relationships, and those relationships are called the pure precession relationships. And then we dealt with perturbations. And here we have a state or a group of states that we know and love and understand, and it gets hit by some evil perturber. And from the pattern of interactions, we can learn the symmetry of the perturber and a lot about the perturbing state. Okay, so this is really setting the stage for, okay, it doesn't have to be only a local perturber. It doesn't have to be a state that's outside of the family of states that we are interested in. It can be, an intruder, but the intruder doesn't actually have to enter the house. It can just mess around with the computer programs. So we're generalizing now on perturbations, and we're going to say, okay, all states, all electronic states, all vibrational states, can in principle interact with this small group of states that we're getting our PhD on. And so we want to build a model that will deal with this infinity of other states without having to do an infinity of work. Because we're smart. Molecules are stupid. Okay, and so the procedure for doing this is called the Van Vleck transformation. And it's basically second-order perturbation theory done ad infinitum. I can't use, yeah, I won't even, okay. So what we're going to do is we're going to look at several kinds of corrections. One is we think of rotational constants, which come from the rotational operator, where there is a 1 over r squared in the denominator. That's an explicitly r-dependent operator. And we get from doing second-order perturbation theory on operators of this form, we get centrifugal distortion constants. Instead of centrifugal distortion operators, we get constants that are v-dependent, and we get this from the form of this operator. We have operators, we have spin orbit constants, which are implicitly r-dependent. This is explicitly, this is implicitly. It's an electronic property. Any electronic property is a function of internuclear distance. So it's implicitly r-dependent. And from allowing there to be an implicit r-dependence, one is able to determine parameters that correspond to the centrifugal distortion of A. One also can, from this sort of analysis, before we do second-order perturbation theory, we can determine B of V, the vibration dependence of the rotational constant, and A of V, the vibration dependence of the spin orbit constant. But this is the next step that you didn't know how to do, and so that's what we're going to be talking about. And then there's going to be things called lambda doubling. And lambda doubling comes from sigma states. So all non-sigma states interact with sigma states, and as a result, the parity, or the EF doubling of all states with lambda not equal to 0 is lifted a little bit, and it's always due to sigma states. And so we're going to understand centrifugal distortion of constants like the spin orbit constant, and lambda doubling constants by doing this Van Vleck transformation. And for my example, I'm going to describe exclusively doublet pi and doublet sigma states, because again, that's the minimum complexity that I can use to illustrate all of this stuff. And then you, of course, are charged with the responsibility of doing something terrible. But you know, I've outsmarted myself, because sextet delta states will have unbelievably small and unbelievably complicated lambda doublings, and I just don't have the heart to ask you to do that. So, but we'll see. I'm going to come up with something. Okay, so we're going to have a procedure which is basically second-order perturbation theory. And what we're going to do is we're going to write a Hamiltonian in terms of the original constants that we understand, and some new ones, which are functions of V and J, and these functions of, so this, we're going to derive these functions of V and J. And they're going to be multiplying some matrix elements. Okay, so this looks like matrix multiplication. It is. But it's also second order perturbation theory. So we have a product of two matrix elements and an energy denominator. And so all of the new things are going to be some explicitly calculated function of V and J, and something here which we're going to call, say, P or Q or O or lambda or gamma or AD or D. So this thing will be the second order parameter that enables us to define a Hamiltonian that fits the spectra to as high an accuracy as we care about. And so we might have to generate more than just a first cut of these sorts of parameters, but usually what I'm going to describe will be sufficient. Okay, so let's start out by writing the effective Hamiltonian, not the effective Hamiltonian, the Hamiltonian for our doublet pi 3/2, 1/2. We've done this before. And this S just means plus or minus. And since we can have sigma states of both sigma plus and sigma minus forms, even though the sigma minus ones are relatively rare compared to the sigma plus, I mean, they're not, you're going to encounter them. The ground state of oxygen, for example, is a triplet sigma minus state. So it's not as rare as you might like. But anyway, we just need to include that for generality. Okay, so if we had a world in which there was only a doublet pi state and a doublet sigma state, then this would be the effective Hamiltonian that I'm going to write down. You already have seen something like this. So we have the energy for the vibrational level of the pi state. And then we have I'm going to stop putting pi's on thing, a over 2, because this is double pi 3/2, and the spin orbit is a LZ SC, and L is 1. LZ gives you lambda of 1, and SC gives sigma of 1/2, and so we get plus 1/2 A and minus 1/2 A. And then we have B, I have to put a pi on it here, y squared minus 2. Sorry about that. Well, what am I going to do? I'm going to move that over. You won't catch Sylvia Sayer ever making a mistake on a blackboard. But I make mistakes on the blackboard.
Yes.
Yes. See, I make mistakes even when I'm making mistakes. All right, so the diagonal element here is going to be E V pi minus A over 2 plus B pi, and we have just y squared. So already there's something a little bit alarming that somebody had to be clever in figuring out what goes here, and it's not the same. It's not B JJ plus 1, or it's not B NN plus 1. It's something different for the different omegas. And then for the sigma state, we have E V sigma plus B sigma V sigma, sorry, y squared minus or plus minus 1 to the S y. Okay, so this complexity comes from the fact that we went to the parity basis, or the EF basis, and we get, whenever we have states that go on both sides of where a simple ladder operator can take you from a positive value of the projection quantum number to the negative value, we get this kind of stuff. because we take the sum and difference of positive and negative projection quantum numbers. And if there's a term in the Hamiltonian that can cross 0, then you always get this sort of thing. But it never happens here because you can't cross 0 without changing two things. Okay, so now we have the off-diagonal elements, and in here we just have minus b v pi times y squared minus 1 square root. And again, you know, we have three different functions of the rotational constant appears in three different places with three different coefficients. Remember, y is j plus a half. And it's just convenient to not have to write j plus half all the time. And then we have an off-diagonal matrix element between doublet pi 3/2 and doublet sigma. And so that has to be a change in omega of 1. And so it has to be entirely j-dependent. So we have the term that can do that is the rotational Hamiltonian. And so we have this beta to suggest rotation. And so we have v pi, v sigma, and then it's 1 minus, I'm sorry, it's y squared minus 1 square root. Okay, and in this location we're going to have, because it's doublet pi 1/2, we're going to have, and we're going to go to doublet sigma 1/2 or doublet sigma minus a half. There's going to be a b-type term for the change in omega and an a-type term for the not change in omega. And so what we get here is alpha s, because it could be a sigma plus or a sigma minus state, plus beta s. Now I've omitted the v pi v sigma. These things are some operator times a vibrational overlap integral involving that, but you don't need to bother with that garbage. Okay, that was just my PhD thesis. Okay, so this is the matrix we're going to be using. It's the doublet pi doublet sigma, or the pure precession Hamiltonian. Well, it isn't pure precession because I haven't simplified these. It's just a doublet pi doublet sigma. Okay. And we're going to use this a lot. I didn't include spin rotation just because it's small and because it would just make things too tedious. I didn't include spin-spin because it's 0 for doublet states. Because doublet states, one spin. You can't have spin-spin because there's only one. Okay, so now this is the world. We have the world that's divided up. It's an infinite matrix. And we have a little block that's interesting. And we have a very large block that's not interesting. And so let's just indicate that this little block has indices m. And the big block has indices n. And so we don't care about this because we're not doing any experiments on the states in this block. All of our experiments are in this block. The big problem is they are connected by stuff in here. It's not 0. And so we have to figure out a way to fold the effects of these states into this block. And all of the stuff that we're going to be folding lives here. So, you already know in a simple one-dimensional world how to deal with states far away. And that's second-order perturbation theory. So you know you're going to have things like this. You're going to have a correction to the vibrational level. You've done this. You did some homeworks. You're going to have corrections that will have the form h prime v prime squared E0 v minus E0 v prime. So there are going to be correction terms in a one-dimensional problem, which will just be from second-order perturbation theory. Matrix element squared, over energy difference, zero order energy difference. And the problem is this block is not just a bunch of diagonal elements. There are off-diagonal elements. And we have to know how to correct the off-diagonal elements as well as the diagonal elements. Now there's an elaborate procedure that enables us to fold all of the effects of an infinite number of out-of-block states into here. And it's basically the same thing as this with a tiny little generalization. And I think that the best way to understand this is, rather than looking at the derivation, just say, yeah, I can sort of understand why it ought to come out that way, and then learn how to derive the terms that implement the correction. And so that's what I'm going to do. And if you don't like it, you can look in my book, you can look in Annalise's paper and Sam's paper, but okay, so what we want to do is what's called the Van Vleck transformation. Van Vleck was a professor at Harvard who knew all the train schedules in the world. But he also was a very smart man in addition to being fascinated by trains.
And Japanese print block. Right?
I didn't know about that, but I knew about the trains because you just generally go to talk to him and he'd find the most ingenious way for you to get from here to there. And no train.
In Boston?
No, from here to somewhere outside of Boston. Well, probably inside Boston too. But nothing is on top. So another thing is that Van Vleck gave his last lecture a few years after I was a graduate student, and I could have gone to it. But I'm stupid. But you're going to my last lectures at this class. So I don't know. I don't mean to compare myself to Van Vleck or anything like that. But okay, so the Van Vleck transformation was, and we'll put a VV on it for the time being, and it's basically telling you what to do about the block that you care about, which is the M block, and you don't care about the N block. Or you could use some other symbol for distinguishing the two blocks. And so what do? Well, you have the zero order energy levels, and well, why don't I be clever? Why don't I be cute? Okay, so that's the same thing as a Kronecker delta. And it just said, okay, here's a constant, and here's a bra and a cat, and if you want to take anything other than the MM matrix element of that, you get 0. It's an elegant way, because this way you can write a matrix as an equation. And I think it's called second quantization, and it's kind of a neat thing. Okay, so then the next term will be a term to the first power of this sorting parameter, and you know how to do that from perturbation theory. And so we have a matrix element, H prime, M prime, and that looks like that. So this is a number, and this just tells you where it goes in the matrix, or if you want to write this out as an equation. Okay, and then the lambda squared term, and okay, I'm going to do it up here. I don't want to waste a lot of space because I want to leave a lot of stuff. Okay, the lambda squared term, and this is what you have to take on faith. But it will look so much like what you expect from second order perturbation theory that I doubt that anyone will have a serious guilt at not deriving it. Okay, so we have a lambda squared over 2 and a sum over states in the N block. And So I'll put out in front. So this is which matrix element it's going to be. And then we have H prime M N, H prime N M prime over E0 M minus E0 N, and then another term. Same numerator, same cofactor over here. Okay, so what we're doing is we have a sum now over all of the remote states. And since we have two different initial states that are close together, we write an expression which is symmetric in those two different states. Now, the important thing is that these two terms are nearly the same, because this is a very large number compared to EM minus EM prime. So what you do is you say, okay, I'm going to combine these two terms. And so we'll get twice, we'll get rid of this 2 here. We're going to combine these, and we're going to rewrite things. And I'm going to commit the worst crime of all, which is to just erase something rather than write it again, because I don't have room. And certain people would never make that terrible crime. So we have E0M plus E0M prime over 2, the average of the two. It's basically this, either one minus En0. So we lost the 2 because we took two terms which are nearly the same, and formally we just choose the, and it's a very good approximation. And this is what you need to now generate all of the corrections that you need to write an effective Hamiltonian. So you have oh, I see. I started down here and I continued up here. So you have the diagonal term, the first order off-diagonal term within the M block, which you already knew about. That was already there. And then you have the off-diagonal in M. Well, actually, it's general. You could have off-diagonal or diagonal. And this is the general form. OK, so that's what we're going to want to deal with. And now, so we have several kinds of terms in the Hamiltonian. The Hamiltonian has not been too terribly defaced. It's been it's pretty well defaced. We have rotational terms and spin orbit terms, and off diagonal in rotation. So what we're going to discover is that when we're calculating matrix elements of the perturbation parameter, we're going to have the rotational part squared, and that's going to give rise to two kinds of terms, EF dependent terms, and that gives lambda doubling, and EF independent, and that gives rise to D, centrifugal distortion. And we have spin orbit squared, and that will give rise to EF dependent, and now lambda doubling, and EF independent, that'll give rise to lambda and AD, those sorts of things. And the parameter that we get, the lambda doubling parameter we get from spin orbit squared is called little o, and the parameter we get from rotation squared is called little q, and then we have cross terms. And again, we'll have EF dependent and EF independent. And the EF dependent, again, lambda doubling, and the cross term is called P. And the EF independent is going to be gamma, as well as correction, AD, etc. here. Okay, so you know that, basically the Hamiltonian is spin orbit plus rotation, rotation squared, that gives rise to certain things, spin orbit squared, and cross terms. Cross terms are really nice because they have signs in them, and these things have signs suppressed, and so they actually reveal things about electronic structure that these can't. Okay. So now what you do is you, is you develop a diagrammatic method for keeping track of all the terms. And it's not a very elegant diagrammatic method, and I call them railroad diagrams just because we start and we have a starting point and an ending point, and we have many tracks to get from one to the other. And so what we do is we say, okay, each diagram describes one matrix element, one location in the M block matrix. And so let us be specific. Let's consider doublet pi 1/2 v pi and doublet pi 1/2 v pi. We have, this Hamiltonian has 6 locations in it that we're going to have to work through the matrix elements for. So let's start with one of them. And so what you do is you say, okay, these are the initial and final states. And now what I want to do is list in the middle all the states to which we could conceivably get by the terms we have available. And so first of all, there is no term in the Hamiltonian that can change anything by more than 1. So you can't change lambda by more than 1. You can't change omega by more than 1. You can't change spin or sigma. And we're going to work we're going to consider mostly just the doublet pi and doublet sigma space. So if we start here, we could get to doublet pi 3/2, and we could get to all vibrational levels of doublet pi 3/2. And so this is one of the intermediate destinations in this path. I can see I'm already doing it. Let me do it in the same way as it appears in the notes. So that's one. Another destination would be this. Another destination would be doublet sigma S V sigma prime. And then there are all other states. But all other states are really not very interesting because most of the effects that we need are generated by just the doublet pi and doublet sigma. But you can extend the techniques to other states. And in particular, what other states could there be? Well, the highest you could go would be delta and quartet. So you could have doublet pi sigma, and delta, quartet pi, sigma, and delta. But a lot of that is really simple. Okay, so then you've drawn now the intermediate stops. Okay, and I've drawn relatively long lines here, because what you do here is you write down what is the matrix element between this and this. You write it here, and here, and here, and here. And then you multiply the two steps, and you put an appropriate energy denominator, and that's done. You're done. You've got it. And so it's a tedious procedure, but for diatomic molecules, it's not too bad. But it's not recommended for polyatomic vibrations when there's more than a couple of vibrational modes, because you can get lost. And the number of possible paths is not diagrammable on a single piece of paper unless you're pretty clever. And so this is an introduction to what is used for polyatomic vibrations, which is usually called the contact transformation. And that just means that Mr. Contact and Mr. Van Vleck never spoke to each other, and so they both thought that they invented something. But Mr. Contact wasn't really a person. He was an Amat and Nielsen, and there's another person. And so there was a procedure developed for polyatomic molecules, which is essentially the same as the Van Vleck transformation, but it was used in slightly different ways, and it was always called the contact transformation, but it's basically the same thing. But you would very rarely use these diagrams because there's so many possibilities. Okay, so we have a matrix up here. You can write the matrix elements here, and then you can combine them. And so I'm going to skip. I'm not going to write them in. But you have to be really careful because, well, for here, when you're going between the same initial and final state, there's no problem because what's here is here. So you're just squaring things. But if you were going, say, doublet pi 1/2 to doublet pi 3/2, then you never have the same thing on the left and the right. And you have to be careful to take all paths, including the same path, but in the opposite direction. And so you can end up, if you're not careful, you can miss a term, and you'll see. But it's only for the off diagonal. Okay, so we do this, and the second order correction to the Hamiltonian in the doublet pi 1/2, 1/2 block EF. That just comes, we have a sum over the remote pi states, and then we get from this we get a b squared y/4. Okay, from this we get a b squared y² minus 1. So when we do that, we see that we have a b, v, v prime, and we have a y/4 from one of the terms, and a y² minus 1 from the other. Okay, and we have a minus a/2 squared. So that's going to be and then we have a cross term. We have a cross term between the a/2 and the b pi. And so that's going to be an a, b. The 2 gets canceled because there's 2 of them. ABY². And we normally don't bother specifying, well, we do specify pi, but we don't specify omega. Because usually the state that's far away is far away compared to the spin-orbit splitting. The vibrational interval, or the vibrational electronic interval, is usually large compared to spin-orbit. So let's just leave this. Okay, but sometimes the spin orbit is large compared to the vibrational interval. Then you have to be a little more careful. Okay, so that's one of the terms, one of the 6 terms that you need to derive for the effective Hamiltonian that's been corrected for all remote pi states and all remote sigma states. And so I do that. But then what you see is there's terms. Here is a term. Whoops. A b squared, a b v prime squared over an energy denominator. And so we're going to call that, the sum over all of them, we're going to call that minus the centrifugal distortion constant. Okay, and so we're going to have now, this term is going to have minus the centrifugal distortion constant times this function of quantum numbers. And this one, a squared v prime, that is going to be called a 0. And what that's going to do is that's going to, it's really going to have a v dependence, a0 v. And so this will give you the v dependence of the spin orbit constant, we call it. And this cross term is going to, well, it has the form of the lambda doubling constant, which is an a times b, and so it's going to look like a p term. And so we define all of these things, a, d, a, 0, v, o, p, q, and we could define gamma and lambda if there were a lambda, but so they're all defined in this way. Okay, so we're not done yet, although Mr. Clock says we are almost done. So we set up this full matrix, and you can do that. And then you do some work on it to organize it. And so on page 6, after the non-lecture stuff, there is just the centrifugal distortion, just the second order constants. And so the important thing to see is that in the double pi 3/2, double pi, whatever. So let's just look at the diagonal locations. We have minus d pi. Notice we call this quantity minus d. That's positive. This is the, let's say this is the ground state. Then this is a higher state, so the denominator is negative. So if we call this thing minus d, then when we put minus d over here, it makes an overall negative. If we call this is negative, if this is minus d, then d is positive. Then we go over here, and we have a positive d, and it has the effect of making the rotational constant smaller. And so that's what that's all about. And so we have y to the fourth minus 3y squared plus 3. And in this location, we have minus d pi y to the fourth plus y squared minus 1. And in this location, we have minus d sigma times y to the fourth minus or plus 2y cubed plus y squared. So the first thing to point out is this doesn't look like treating the centrifugal distortion by saying, oh, well, every place we have B, we replace B by, the standard textbook prescription is we replace B by B minus D JJ plus 1. And if you were to do that, you would get the wrong answer. I mean, the expectation is, you know, the centrifugal distortion is D minus D times JJ plus 1, the quantity squared, because B is the rotational energy is B JJ plus 1. This is close. It is, you know, each one of these has y to the fourth, but it's not the same. And this plus or minus actually, when you do something clever, that goes away and gives rise to something that's unsurprising. But anyway, so what it does, this Van Vleck transformation gives you the correct quantum number dependence of all the terms. And it's not what you naively expect, and that means it's going to fit better. If you have something that's physically wrong but makes sense, well, you're going to need more parameters. But if there's something that's physically right and makes you say, oh, I wish I understood why these things, well, you do understand now. Then you don't need as many parameters to represent the measurements to measurement accuracy, and that's good. And Annalise knows what I call that. Parametrically parsimonious.
I know that too.
Yeah, I know, but you. Yeah. Okay, so I think I should stop. I just want to tell you that I'm not going to follow the path for the next 2 lectures that have been advertised. Next time, I'm going to come back to the vector model and harvest some useful stuff, because I said some things, but I didn't do it properly. And I'm also going to talk about 3J coefficients and talk about angular momentum transformations and pattern-forming quantum numbers. I need to say more on that subject. So Wednesday, I'll do more on that subject. This completely new lecture. I'm writing it for you. You know, there's nothing I can do from 1994 that I can use. I have to do this, and it's hard. I'm tired and an old man, but I'm going to do it. And then on Thursday, I'm going to do for RKR. And so rather than splitting polyatomic rotation into Thursday and Monday, I'm going to bring in RKR. We're saving it for a rainy day, and let's hope it's not raining, but we'll use it on Thursday morning. Sir?
Okay. So maybe this is a philosophical question, but why is it always better to be parametrically parsimonious? That is to say, we just want actual physicality.
Well, but we can't have it, because physicality would involve a full dimensional matrix. And we never would have enough information in a finite spectrum to determine all the parameters. So if you can't have the full truth and nothing but the truth, you back down to something which is as compact and I mean, you're going to have a relatively small data set. Small, you always want more. And so you would like to make sure that every scrap of data, and often you have state, you don't have a contiguous block of states, you have some outliers that just happen to come into your possession. And you'd like to be able to use all of that and to extrapolate well. And so if you have a bad model, it's going to require more parameters to fit it, and probably more parameters than your data justify. And if you don't do that, then it's going to not extrapolate or interpolate. And so you really want to have built in as much truth as you can, because then you get the most bang for the buck with your data.
Okay, let me ask a related question.
Yeah.
So because we have this creed that we fit to measurement accuracy.
Yes.
Right? Imagine that I take the same spectrum, once a decade, with improving technology and all sorts of things. So I get, maybe an order of magnitude. I don't know if that's too much, but you get more and more accurate spectra each time. Does the model that one has to use to reproduce measurement accuracy sort of scale smoothly as I increase measurement accuracy? Then I need another parameter now, or is there some massive shift?
There is a rational procedure, and you don't have to throw out the baby with the bathwater.
Never heard that one before.
So, yeah, if your data is more extensive and more accurate, you do have to include more terms in the Van Vleck transformation. You might have to go to a higher order. But the terms you've already fitted, they don't, I mean, their values might change a little, but their structure in the matrix is not changed. And so...
So, is that really true?
Yeah.
How do you know that that's really true?
Well,
I mean, that would be great if it was really true. But I guess I want to know how one knows that that's true.
well, we basically have order sorting. And so now order sorting is a dangerous thing, because it gives you the sense that you're on secure ground, and you're not, because the energy denominators can be large or small, and the things you're sorting are in the numerator. And so you have to watch yourself. But there's a procedure for saying, okay, these are the terms that you need to consider next. And then order sorting, I mean, then a little bit of looking at the denominators says, okay, we have to include a few terms of higher order that shouldn't have been there, just because there's a subset of energy denominators that are anomalously small. So your order sorting leads you to know where you have to patch the model. It's not a random patch, it's a very much directed patch. And then you know that you're preserving the physical nature. Dick Zare liked to talk about separating the mechanical from the magnetic properties of the parameters. I like that at the beginning, but I don't really know what's mechanical and what's magnetic. Really you have microscopic parameters and then you have these second order things. And these second order things, there's a lot of them, but usually you can keep them pretty pure. And so I don't know whether I answered your question.
I think order sorting answers it.
Okay. Always give a long-winded answer for...
Long-winded question.
Yeah. Well.